Hi, I'm Rahul Ramachandran from NASA's Marshall Space Flight Center. I manage a project called Impact, focused on maximizing the use of NASA's Earth science data. As most of you know, one of NASA's science missions is to study Earth as an interconnected system using instruments on satellites, airborne assets, and other observing platforms. NASA holds the most extensive data archive of Earth observations. The data archive contains 35,000 different data sets, over 500 million data files, and is growing exponentially. The data archive is open and serves the entire global science community. The goal of the Knowledge Discovery Framework, KDF, challenge is to develop a new methodology for our data users to search this vast archive to identify different kinds of phenomena and unusual patterns in the data. The methodology must be general purpose and work on a wide variety of phenomena and patterns. This new kind of search would go beyond what exists today and potentially serve as a useful discovery tool to accelerate science. I would now like to introduce the team.
Thank you. Hello, everyone. Thank you for coming. We are the Knowledge Discovery Framework team. From left to right on the satellites are the researchers, Satyarth, Megs, me, Francesco, and Nishan. Then down on Earth are our project mentors, Anna Maria, Aniru, and Hesham. Our challenge goal was to create a generalized reverse image search algorithm for remote sensing phenomena. Earth observations, or EO, have revolutionized Earth science by providing data at unprecedented temporal and spatial scales. Yet, imagine searching through 33 petabytes or 660,000 Blu-ray discs of unlabeled remote sensing data for one particular phenomenon. Keep in mind that this number is expected to increase sevenfold at minimum in the next 30 years. So we set out to build a general algorithm that could search for these dozens of petabytes of data. So how would such a system look? Let's say that I'm a researcher studying the interplay between hurricanes and dust storms. My first step would be to download every hurricane event within those 33 petabytes of data. While some storms are cataloged, they are few and far in between. Ideally, I would input a query image of a hurricane into the KDF algorithm, and it would search the NASA EO data and return all examples of hurricanes. Then, I could use the very same algorithm to obtain all records of dust storms from a different query image. Such an algorithm would be able to return other phenomena such as wildfires, volcanic eruptions, or even particular cloud formations. So why hasn't this been done before? Well, there are several challenges that hinder generality. The first is the scarcity of remote sensing images which are labeled. Labeling data is typically very time-consuming and expensive. This requires the algorithm to be self-supervised, in other words, without human input. Another challenge is accurately assessing scaling between different phenomena. For example, hurricanes are 500 kilometers across on average, while a small wildfire could be less than 1 kilometer squared. While this problem has been addressed in typical machine learning object detection, it has proven to be elusive in remote sensing data.
Lastly, phenomena might require different spectral bands and resolutions to distinguish events and objects. For example, hurricanes can be detected using a single band of near-infrared, while dust storms require more bands. For other phenomena, such as coral reefs, red, green, and blue channels might need to be supplemented by additional bands. The KDF user-friendly EO similarity search engine requires a robust featurizer. Our featurizer used an image reconstruction autoencoder as a self-supervised convolution neural network. This featurizer will be publicly available and can be used as a base model during transfer learning for developing remote sensing computer vision classifiers. To evaluate our featurizer, we used two test cases, a curated hurricane dataset from GOES and a realistic dust storm dataset from MODIS. Labels were not used while training this featurizer in either test case, allowing us to assess how well our self-supervision network can perform in the absence of labels. The hurricane dataset featured images with hurricanes of different categories. The hurricanes were centered on the image and absent of any sensor artifacts, whereas the realistic dataset represented one region on the western coast of the Sahara and included many artifacts such as no data strips and clouds. Furthermore, land features are often visible through the storms, while hurricanes are not transparent. The dust storms captured in the realistic dataset were often at a much larger scale than the hurricanes. Lastly, the hurricane dataset only used one spectral band, while the dust storm dataset used red, green, and blue.
Okay, so as mentioned, we use image reconstruction autoencoder as our self-supervised module. Since we do not have labels, we cannot have a supervised learning module. So we generate our own kind of labels and have a self-supervised module instead. An image reconstructor autoencoder tries to reconstruct its input image. Autoencoder, by definition, is a kind of deep learning architecture that consists of two subsections. One, the encoder, that transforms the input to the smallest resolution feature vector that Nishan talked about. And second, the decoder, that tries to reconstruct the image from its feature vector. This feature vector is a higher dimensional representation in terms of channels of the image. The reconstructed image is in a way a piece of visual evidence that the features successfully capture the prominent properties of the input image. Now, given that we have our featurizer working, the next question is, how good is our generalized featurizer when finding similar images? Here, we demonstrate our similarity search on a tropical storm image. That is in the top row. The wind speeds are measured in knots. The left image is the query image, and the images to the right are the three most similar images, or the three nearest neighbors according to our featurizer. We can see that for this example, the hurricane featurizer found the majority of the hurricanes of the same category. And even the one that is misclassified comes pretty close in terms of wind speeds. This meaning that the featurizer captured this correlation between the hurricanes in the unlabeled data. We used accuracy at K to quantify how frequently the similarity search finds images within the same category of the query image. The x-axis represents the number of nearest neighbors, or the number of similar images returned. The y-axis represents the percentage of times the nth nearest neighbor returned image within the same category as the query image. For the 5 nearest neighbors, the featurizer had 45 to 90% accuracy, meaning that our featurizer worked well on the hurricane dataset.
But what happens when we test the featurizer on a realistic dataset? The hurricane dataset was an ideal test piece as the hurricane is the only feature in the image. But the dust dataset is a bit messier, as we have other objects within the images, such as continent edges, clouds, and no data strips. As shown in the top row of images, the query image of the dust storm on the left returned images with both dust and no dust. As we can see from the accuracy at K graph below, the featurizer was half as accurate predicting dust storms as it was predicting hurricanes category. In conclusion, we were able to obtain meaningful search results using the same featurizer and similarity search algorithms for two diverse atmospheric phenomena in the absence of labels. The curated hurricane dataset is ideal for testing the featurizer due to its reduced complexity, but it may not reflect the reality of remote sensing data. The dust storm results demonstrated that featurizer accuracy is highly dependent on the appearance of the phenomena and the data quality. The challenges we faced adapting the featurizer to the dust dataset are not unique for this phenomenon. So developing a general featurizer that works without labels will require us to resolve challenges regarding the focus, scale, and spectral resolution of the dataset. The Earth system is undergoing rapid change. Direct and indirect human activities have resulted in desertification, increased intensity of hurricanes, bleaching of coral reefs, and other large-scale environmental changes. Earth observations are a means of studying environmental hazards and can aid in conservation decision-making. Yet those decisions and scientific breakthroughs may be buried in 33 petabytes of archived data. Our general featurizer takes one step towards a robust, user-friendly tool that provides the necessary data to the people who can make the most difference. With that, we'd like to thank everyone for their time and all of the people who have helped support us, especially Raul and the Impact team.
Great. Thank you, Knowledge Discovery Framework team. And I'd love to invite our panelists and all of our team from the Knowledge Discovery Framework back on. So for this round, I'd like to ask our panelists, what is one thing that this search capability enables? So to kick us off, I'll turn it to Scott.
This is at Google, this is the next generation of search, where it's called semantic search. There's far more unlabeled data than labeled data. And these sort of techniques we're actually using at Google, and is implications across all kinds of industries for video and imagery.
Great, thank you, Scott. And Aaron.
Yeah, so as I mentioned, this is 33 petabytes of Earth science data. As the authors mentioned, this is 660,000 Blu-ray discs, or 67,200 years of MP3 music. So this is an exorbitant amount of data. So what it does is it really enables us to bring to light and make sense of all types of Earth science data, from the top of the atmosphere to our deep oceans.
Thanks,
Really
Aaron.
exciting.
Yeah, great. And Rodney.
So the one thing that came to mind here, where I think, what this work can really help to inform and enable, is a deeper understanding of a phenomena that I recently, in the past few years, just became aware of, not being an earth scientist myself, called teleconnections. And I guess it's sort of a term in atmospheric sciences that refers to climate anomalies that are related to each other at very large distances that might otherwise seem unrelated. So really think that, again, a deeper understanding of that whole phenomena could potentially be an area where this work can be brought to bear upon.
Thanks, Rodney. That's a great add. And now I'd like to thank the Knowledge Discovery Framework team and our panelists. This was great. Up next is our last team of the day, the